Okay, thank you all. And today my talk title is Dynamics of Gaseous Detonations with Lateral strain rates. As it's known, detonation waves are self-sustained supersonic combustion waves, which propagate in the order of several kilometers per second. The large overpressures generated behind gaseous detonations make them attractive and useful for developing propulsion systems. However, realizing all these practical applications requires predictability of the detonation behavior. In practice, detonation waves are usually subject to lateral strain. An important scenario is related with detonations in small-sized confined geometries. For example, for detonations in narrow channels, they usually propagate with significant boundary layer losses. In the shock-attached frame of reference, the boundary layer acts as a sink by removing the mass from the main flow. Equivalent to the in this core flow, the channel seems to have enlarged cross-section whose area increase can be modeled by the negative boundary layer displacement. Lateral strain has been well known to decrease detonation propagation speeds and also impact the propagation limits by extinguishing detonations. Thus, in order to achieve the practical purposes of either utilizing or avoiding detonations, effect of lateral strain on detonation dynamics needs to be quantified and predicted. The prediction of the detonation dynamics at present mainly relies on the extended ZND model with lateral strain, which can be obtained by incorporating the lateral strain rates into the classical ZND model. Despite the 1D steady ZND model description, detonations in real gases actually take on much more complicated cellular structures, as shown from the experimentally visualized structures of detonations for two different mixtures. On the left is the hydrogen-oxygen-argon detonation, while the right show is methane-oxygen detonation. As compared to the piecewise laminar structure of hydrogen-oxygen-argon detonations on the left, methane-oxygen detonations on the right appear to be highly turbulent and characterized by significant unreacted gas pockets. According to the regularity of detonation cells, detonations can be classified into regular ones and irregular ones. Typically, the regular detonations are characterized by mixtures with high argon dilutions and tend to be weakly unstable. While for the irregular ones, they are characteristic of hydrocarbon-oxygen mixtures with high activation energy and being more unstable. In order to quantify the response of detonation dynamics to lateral strain, recently Bozu proposed a novel experimental method which involves a pair of exponentially diverging ramps, as shown in the figure here. The key feature of the ramp is to have the logarithmic area divergence rate as a constant here. This constant divergence rate can enable detonations to propagate in quasi-state with a constant mean lateral flow divergence. As a result, the relationship between the mean detonation propagation speed and the lateral flow divergence can be precisely evaluated. It then permits meaningful comparisons between experiments and the model predictions. In their experiments, two mixtures of different regularity were tested, namely the weakly unstable argon diluted acetylene oxygen detonations and the highly unstable propane oxygen detonations. Their comparisons, as shown in the two figures in the figure, the points are the experiments, while the lines are the model predictions. The comparison shows that while the experiments disagree with the model predictions, the weakly unstable argon diluted acetylene oxygen detonations show a better agreement in general. Although the previous works have showed that the generalized ZND model can relatively well predict the weakly unstable detonation dynamics and failed for the highly unstable detonations. However, whether there is a link of departure between experiments and the ZND model predictions to detonation instability is still not clear. The second question is, how can we improve and make corrections to the ZND model predictions of the unstable detonation dynamics? Moreover, since in experiments, it is very hard to evaluate the effect of lateral strain on the unsteady 2D detonation structures. Thus, further understanding of the effect of lateral divergence on cellular detonation dynamics by numerical modeling is necessary. Therefore, the present work aims to address these questions from both the experimental and numerical modeling perspectives. In experiments, the well-defined exponential Hall technique has been extended to a range of characteristic mixtures with varied levels of detonation stability. While for the numerical part, this work formulates a model for evaluating the effect of boundary layer losses on the 2D detonation cellular structures. This part, now let's go to the first part. This part focuses on the very regular hydrogen-oxygen-argon detonations and aims to verify whether the ZND model can predict the detonation dynamics of the weakly unstable hydrogen-oxygen-argon system. Here shows the experimental setup, which involves the 3 sections. For the test section, the detonation evolution process was visualized through shadow graph or chenille techniques. In these experiments, 2 ramps of different area divergence rates were adopted. The test mixtures were stoichiometric hydrogen-oxygen with 4 argon dilutions. Here shows the experimentally obtained detonation fronts at different time instants, which I superimposed together here. The detonation propagates from left to right. When the initial pressure is relatively high, as shown in figure A, the detonations propagate in quasi-steady conditions with a constant mean front curvature, as can be seen from the very good agreement between the experimentally obtained detonation front and the quasi-1D approximation. However, as denoted by the red dashed lines, the red dashed lines represent the quasi-1D approximation. However, when the initial pressure is decreased, the cellular structure is enlarged, and near the propagation limit, as shown in figure B, detonation propagate in a single-head manner, organized with a transverse detonation. In the ramp experiments, the total flow divergence includes 2 paths. The first comes from the geometrical area divergence of the ramp, and the second one is due to the boundary layer induced flow divergence from the lateral side walls. By collapsing the experimental data of both the large and the small ramp, one can obtain the unique decay relation between the velocity deficit and the lateral flow divergence. As a result, the boundary layer induced lateral strain rate, VBL, can be derived. For example, for hydrogen-oxygen to argon, as shown in this figure, the boundary layer induced loss rate, VBL, from our experiments, it was found to be about 5.5, which can be varied depending on the mixture. Actually, the relationship between the velocity deficit and the flow divergence can also be obtained by solving the generalized ZND model with lateral strain rates, as shown in this set of ODE. In this work, in all the calculations, the detailed San Diego mechanism was used for describing the chemical kinetics. Here shows the comparisons between experiments and the generalized DND model predictions in terms of detonation speeds with respect to initial pressures for the mixture of hydrogen to argon, for example. The results show that with the experimentally obtained boundary layer loss rate, FBL, the generalized DND model can excellently predict the experiments, except the minor discrepancies near the limit. Such discrepancies are presumably due to the promotion effects of the strong reactive transversal waves and the enhanced detonation instability near the propagation limit. In addition, this work also evaluated the boundary layer induced lateral strain rate using phase model as shown in the blue dotted line, which slightly over predicts the experimental detonation speed, as can be seen from the blue dotted line. This work then evaluated the Reynolds number behind the detonations and found that the boundary layer behind hydrogen-oxygen-argon detonations is probably laminar. Thus, phase assumption of turbulent boundary layers behind the detonations is questionable. Finally, this work proposed to apply Mirels' shock-induced laminar boundary layer theory for evaluating the boundary layer-induced lateral flow divergence as shown in the as shown for the green dashed lines. You can see that both the laminar one and the phase model have the close predictions of the experiments and can relatively well predict the experiments. However, it's still not clear why phase turbulent assumption can still result in such a relatively good prediction of the experiments. Now let's go to the second part. The previous one has verified that the general DND model can excellently predict the experiments. Now let's look at the more unstable hydrocarbon-oxygen detonations with varied levels of detonation instability. For look at the effect of instability on the predictability of the detonation dynamics by the models. And the mixtures involved here is the stoichiometric methane-oxygen, ethane-oxygen, and ethylene-oxygen. Here shows the experiments of the methane-oxygen detonations near the propagation limit. As you can see from the video, an important characteristic of the propagation of the methane-oxygen detonations is the generation of unreacted gas pockets along the turbulent shear layers. Actually, this work also found that evaluate the time scale of the consumption of these pockets and found them to be comparable to the detonation cell time scale, which is much shorter, approximately 4 to 5 orders of magnitude smaller than the shock-induced ignition. Thus, the shock-induced ignition alone cannot explain the combustion of these pockets. Actually, if we look at the video, we could see that the burning of these pockets involved the turbulent diffusion processes. Actually, this also happens for the ethylene oxygen detonations and also ethylene oxygen detonations, as shown in these two figures. You can see the significant unreacted gas pockets. Since these pockets involve the burning of turbulent combustion, so it is instructive to evaluate the turbulent flame burning velocities. And this work found that these velocities to be 30 to 70 meters per second, which is larger than the corresponding laminar one by a factor of 2 to 7. Then this work also obtained both the experimental and the theoretical decay relationships. Here shows the comparisons between the experiments and the generalized DND model predictions for methane-oxygen detonations as shown here. Clearly, the DND model completely fails to predict the experimental data. While for the ethane-oxygen and the ethane-oxygen detonations here, the DND model can better predict the experiment for small divergence and the velocity deficits as compared to methane-oxygen. However, the model underpredicts the limited divergence rates by a factor of approximately 2. Then this work quantified the departure of experiments from the theoretical predictions in terms of the near-limit detonation dynamics for each mixture, as shown in Figure A. This figure demonstrates the ratio of the experimentally obtained limiting divergence to the DND model predicted value as a function of the instability level. We can see that from this figure. As the detonation instability value increases from the lowest of hydrogen-oxygen-argon to the highest of methane-oxygen, that departure shows a considerably increasing change. Further, this work quantified the departure between the experimentally determined minimum propagation speeds near the propagation limit and those from the DND model. We can clearly see that the experiments and the model predictions show the opposite trend in terms of the instability. Here, the solid points are the experiments, while the empty ones are the empty circles are the DND predicted minimum propagation speed. Therefore, as the detonation instability level increases, departure of the experiments from the DND model increases. Here, it further proposes the departure level defined by departure of the critical flow divergence multiplied by that of the velocity deficit near the propagation limit, as shown in Figure C. The strong dependence of the departure level on instability indicates that the detonation instability chi appears to control the level of predictability of detonation dynamics by the DND model. In addition, this work also evaluated the hydrodynamic reaction dose thickness in the near-limit detonation experiments, and also compared them with the corresponding theoretical lengths as shown in Figure B here. Compared to the weakly unstable hydrogen-oxygen-argon system, the highly unstable methane-oxygen detonation had a much shorter reaction dose thickness, as you can see for the methane-oxygen here. It had much shorter reaction dose lengths observed from experiments than the theoretical value. It thus indicates the existence of additional effects on significantly promoted the combustion in these unstable detonation experiments, and thus decreases the characteristic reaction lengths. A useful formulation of the detonation problem is seeking a macroscopic average description of the detonation structure, such that relevant empirical models can be developed for capturing the detonation dynamics at macro scales. Here, the work extracted the empirical global one-step reaction model from the experimental decay data by fitting the pre-exponential rate constant and the effective activation energy such that the DND model matched with the experiment as shown in this figure. Here, note that the red line represents the DND model prediction with the detailed chemistry, while the blue one dotted line represents the predictions using the calibrated one-step reaction model from the experiments. The table lists the thermochemical parameters for the empirical reaction models. Among these parameters, the last two feeding coefficients of the activation energy and also the reaction rate amplification factor G are worth commenting. Obviously, the effective activation energy for global description is much smaller than the real chemistry decomposition, particularly for methane-oxygen detonations. At the same time, the global rates of energy release are greatly enhanced, as indicated by the reaction rate amplification factor G. While for the less unstable hydrogen-oxygen-argon system, the amplification factor G tends to 1, as shown in Figure A, and also the calibrated effective activation energy are almost the same. Is almost the same with the real chemistry decomposition as can be seen from the Figure B. It is thus clear that the hydrocarbon-oxygen cellular detonations from experiments have a much more enhanced burning mechanism with substantially suppressed thermal character of ignition as compared to the laminar ZND wave. This is realized by the intensified ignition mechanism assisted by the turbulent burning of the Iraq gas pockets as observed in the previous experiments. The previous two paths have experimentally investigated the dynamics of detonations with varied levels of cellular instability subject to lateral strain. However, in these experiments, it's hard to isolate the lateral strain rate for evaluate its effect on the unsteady 2D detonation cell dynamics. Also, directly resolve the boundary layer in 3D Navier-Stokes equations is computationally expensive. Therefore, this part is to propose a novel formulation of a numerical model to evaluate the effect of boundary layer losses on the cellular structures. Before modeling, now let's first look at the problem. Here shows the video of the very regular detonation with a single cell propagating in a straight lateral channel. Due to the boundary layer losses from the lateral side walls, detonation velocity deficit can reach about 20% of DCJ. Therefore, in order to recover the experiments, one needs to consider these significant boundary layer induced losses into simulations. First, this work shows the model the boundary layer losses by model this phenomenon by incorporating the boundary layer losses from the lateral side walls of a lateral channel into the unsteady 2D Euler equations as a source term. The boundary layer induced lateral flow divergence is evaluated using the Mirels model and can be expressed as the simple relation given here. In this relation, Km is the Mirels boundary layer constant, which governs the magnitude of the losses, and the W is the channel width. Note that because in the channel, the channel height is much larger than the channel width direction, which is perpendicular to the perpendicular to our to the plane. So the boundary losses in the channel height direction can be negligible to the other direction. So here W is just the channel width and the nu S is the post-shock kinetic viscosity, and the T minus Ts is the elapsed time since the particle passes the shock. Also, the work adopted the two-step reaction model for describing the chemical kinetics. Note that all the required parameters are calibrated from the detailed chemistry of San Diego mechanism for matching the DND profiles. Here shows the numerically tracked maximum energy release rates for hydrogen-oxygen-argon detonations with different losses. From the simulated results, it can be observed that the detonation cell size becomes larger as a result of increasing the Mirels constant Km. namely increase the magnitude of the boundary layer losses. The present simulations show that when Km equals 1.75, it can very well recover the experiments in terms of both the velocity deficit and also the cell size. However, according to Mirels' theory, the theoretical value for hydrogen-oxygen-argon detonation is supposed to be about 4. Such discrepancy from theoretically computed Km presumably originates from Mirels' assumption of the uniform and steady state behind the shock, while for the detonations, significant gradients of pressure and temperature exist. This probably results in the thinner boundary layers than the Mirels theory. Besides the velocity deficit and the cell size, the experimentally visualized qualitative features of the detonation structures, as well as its cellular dynamics, can be also very well reproduced by the simulations, as shown from the comparison between the experiments in the top column and the simulations in the quantitative simulation in the bottom column. Furthermore, quantitative agreement in temporal velocity evolution at a single cell when compared to experiments was also obtained, as shown in this figure here. This suggests the robustness of the proposed quantitative formulation, as well as the two-step chemistry adopted here in simulating the real detonations in experiments. Finally, this work evaluates the effect of boundary layer losses on the detonation cell dynamics, as shown below. Evidently, the presence of wall losses modifies the cellular dynamics compared to the CJ case. Detonations with losses have larger velocity fluctuations and more rapid decay rates of the lead shock. To summarize, this work first demonstrates the excellent predictability of the hydrogen-oxygen detonation dynamics at the macro scale by the quantity 1D DND model with lateral strain rates. And then it established the link of departure between experiments and the DND model predictions to the detonation instability. Also, it clarifies the role of unreacted gas pockets impacting the dynamics of unstable detonations. Finally, it proposes a novel quantitative approach for realistically modeling detonations with significant wall losses in narrow channels. Okay, thank you.
Thank you very much, Qiang. It's very interesting talk and a lot of informations. So I do have some questions, but I would like to ask the audience first. If anybody else have a question or comments.
Hi, Qiang.
Please feel.
Yeah.
If you go back to slide 38.
38. Okay.
Yeah. So if I'm reading this right, with no losses on the wall, the detonation speed is actually slower at the beginning of the cell than it is than with losses. Do you know? Can you explain that?
Actually, for this phenomenon, we at present what I think is it has two possible reasons, but not confirmed yet. The first one is because if you have losses, because the detonation speed decreases, then the detonation instability would be at the result increased, since the enhanced detonation instability could lead to the decay rates, leads to the larger velocity, the fluctuation of the lead shock. The second possible reason is explanation is possibly because since it has the boundary losses, it probably directly modifies the flow field behind the lead shock. Since since it reduces the flow field, for example, directly decrease the speed. As a result, also impact the dynamics. But which explanation is correct or needs some simulations, but this I haven't done it yet. Yeah.
All right, thanks.
Any other questions? You can either raise your hand in the chat board or the participant manual. Yeah, actually, I have a further question with regard to this single cell measurement. So this is the same. What you are measuring here is the same as in this in this figure, like just along the center line.
Okay.
Like, how did you get that the experimental measurement?
Oh, you mean the cell dynamics?
Yeah,
this
yeah,
one?
yeah.
This one?
Yeah.
Oh,
like
this one.
Yeah.
This one actually is this one. This work has been done by our group member, Chivert Kevin, and he developed a method for reconstructing the speed. He extracted the speed both in the center line and also in the top wall and the bottom wall, and then reconstructed in a cell. But at that time, we just have one experiment. In the beginning of this year, we did we repeated several more experiments, and actually he's refining this work for the experiment for reconstructing the cell dynamics from the experiments, and but I'm not sure how to say it. But for here, it's for one experiment, and was the speed was extracted from both the center line of the cell and also the top and the bottom walls.
Okay.
Yeah.
Okay. But I think like for
limited. Yeah.
Okay, but for I think for very unstable mixture, then this sometimes we can see, even from the suit foil, we can see different cell size.
Yeah.
And is this kind of a cycle? Is it something repeatable, or is this like actually just from I'm just making sure that my understanding is correct. This is like a cycle of a cellular dynamics motion, right? Like a period, and then we'll repeat like this. So we are showing this x versus L is like you normalize the distance.
Normalize, distance, yes.
With respect to maybe one cell size or one cell length. Is that?
Yeah, one cell length. Yeah.
Okay.
For the experiment, actually, it's one cell length. But for the simulation, although for the cells are not but for this work, we got we got the information. We analyzed the information until the cell repeated like for example, for this one is only one cell. We got the stable cell for at least 10 stable cells. 10 stable cells, and then actually we previously I put all the 10 stable cells in this figure, but the time resolution is not as small as this one. then I put the like the when you print you save the file, you need to decrease your time step for saving. Save I choose choose one cell, and then could have more outputs and plotted. Actually, previously I plotted 10 cells, but they are the same. They're almost the same within the range, but it's just a large scatter. Yeah.
Okay. So this is what you call quasi 2D simulations. It's basically, it is two-dimensional simulations, right? You have and then you have this loss term, which this is Km parameter term to represent the boundary layer in the in the depth, like in the transverse direction, like the third direction of the system, right? Okay. Yeah,
the,
just
the boundary layer. The boundary layer on the window is
right.
the way I like to think about it. It's the boundary layer that you're looking through when you look through the window.
Right. Right. Okay. Yeah, just to make sure my understanding is correct. Yeah. Okay. Yeah, I have another question with regard to this like this the ZND model with one-step chemistry or one-step kinetics try to fit to the unstable data. You show this like the as a function of this chi parameter, this fitted activation energy is pretty much this slide. So on the right figure, you show this. I don't know how you define this. This is like a global activation energy, one step that you use the ZND model to fit to the to the experimental data. This remains pretty much constant across a wide range of chi, but this G parameter, which my understanding is like a fitted pre-exponential factor multiplied by the exponential term, right? And this shows a big change. I just didn't really follow the logic why from these two different trends you get the point that this implies that the turbulent burning is the mechanism to assist this second line you wrote here, this statement. What is the logic from these two trends, these two results to get there? I'm not sure if I can follow. Yeah, please.
Okay. Understand. Actually, here first like from the experiments like I showed for the methane-oxygen, like ethylene oxygen, ethylene oxygen, we could see that it indeed produces a significant unreacted gas pockets, and we also found that the consumption of these pockets are much faster than expected by the shock-induced ignition, and we also see that this the pockets burn through the consumption of these pockets involves the like the surface the diffusion processes, and then we evaluated the burning rate of these pockets, and like I showed, I think it showed, and found it's larger than the lambda one by like a factor of 2 to 7, and then for here the for here like for the G, the factor actually in my understanding is like it represents like the reaction rate, the amplification factor. So from this figure, you could see that like the trend is for the hydrogen-oxygen-argon system, the G tends to 1, but for the the methane-oxygen is much larger. So combine what we observed from the experiments and also from this physics, we clarify this as to this work clarifies this to the intensified ignition mechanism due to the turbulent burning of the unreacted gas pockets. Yeah.
Okay. So so if you I don't know, like if you use this fitted G and fitted activation energy, and then you calculate the ignition time of like maybe a constant volume or like a just like a zero-dimensional ignition time, delay time, and how this is compared to the detailed chemistry associated with certain mixtures. Is that like a I mean, like if you use this fitted one-step kinetics to do this to calculate this ignition delay time, and how this ignition delay time are compared to that from Cantera or you know, like any software considering detailed kinetics?
For this comparison, I didn't do this comparison like using the calibrate one-step model for calculate the ignition delay compared to the detailed one. But I think but I'm not sure. But I need to confirm it. But I think it's probably much faster than the. I'm not sure, but I think it's probably much faster. Yeah.
Okay. Okay, great. Yeah. Thank you for your answer. Thank you. Any other questions from the audience?
Yeah, I'd like to, if you can maybe let me share my screen. That's awesome.
Yeah, go ahead. Yeah.
So, my video here. Hi, Qiang. So yeah, as you probably know, I'm a very big fan of your work. I really admired your reading your dissertation. I was on Qiang's committee, and probably also figured out I was some of the reviewers for your journal papers as well. So I've gone through your work many times, and I've always really enjoyed it and learned a lot from it, and most of all, just the results, the movies, and then the way all the data plots together. Just very beautiful work. There's just kind of a question, or I think an issue that I've had with the exponential horn technique, and it's not really a flaw. It's just an issue that I would like to discuss a bit, and I've discussed it with Professor Radulescu, but I think it might be good for us to discuss this a bit. So the technique is you have a detonation in a, you can think of it as in a straight channel. I know in reality you kind of cut into the detonation, but we can just imagine it's in a straight channel, and here comes the detonation wave. I'll draw some detonation cells here and transverse waves. So it's coming this way.
Yeah.
And then we encounter the horn, and let's say we have a very the short one like this. So I'll really exaggerate it like this. I know it doesn't really look like that. Most of your experiments were done with a horn that looks more like this. But let's just imagine for a moment the limit of a very steep horn. Now, when the detonation reaches the corner right here, the expansion starts, and the concept is that while it's expanding through this section, the curvature, which is sort of related to 1 over a dA dx, that this remains constant, and the whole detonation wave is exposed to this same curvature. But the physics is that when the detonation encounters that corner, the detonation up here doesn't know about that corner yet. So the real physics is up here, this detonation is still going absolutely quasi-planar because it doesn't know, and only down here, this region has been affected by the corner that's here. So there's information that has to propagate up. So there's like a zone of influence that propagates up here, and you know, the detonation on the top is just going to continue to be perfectly straight, and only when that information reaches this wall that it still even knows that you know, now the whole detonation knows there's a corner here, but it doesn't really know what the ADX is yet, and this information has to propagate back, and it's really how the detonation responds to that area change would all be determined by acoustic information or characteristic information propagating back and forth. So if the expansion is very, very gradual, so it just slowly expands like this, then you know, you would hope that this information propagates very quickly, and that this assumption is valid, that there's sort of a constant area expansion applied to the flow. But as the ramp starts to get more, the exponential ramp starts to get shorter and shorter, then I think you would need to take the wave information into account, and it is no longer a quasi one-dimensional continuous expansion. So that's an issue, and I would just sort of bring up that this is related to a problem that Xiao and I worked on with the Jinling Li, who's now at Northwest Polytechnical University. We looked at if you have a detonation that is perfectly confined. So you have, let's I'm going to make it really thick here. So you have very heavy confinement of a detonation wave, and then so well. See if I can draw this here. So this is perfect. And also on the bottom, we'll have perfect confinement. And we'll have a detonation wave here. I should make that in red. And then at one point, so we were looking at a detonation wave in a solid explosive, in a condensed phased explosive. And what happens when that confinement ends? So there's very elegant theory for the dynamics of solid explosives, condensed explosives called DSD, detonation shock dynamics.
Yeah.
And it says that the dynamics of the detonation is entirely determined by the local curvature of the wave, and you can then come up with much simpler solutions for the dynamics. So we tried to apply this detonation shock dynamics to this problem, and what it says is that as you reach this point right here where the confinement ends, that the wave starts to experience a curvature, and it can make a prediction as to how the detonation wave propagates. Only the prediction is completely wrong because it misses the fact that when the detonation reaches here, it's still flat, it's still experiencing the confinement, and it takes time. Again, there's a characteristic time for the information of that corner to propagate down, and the detonation shock dynamics theory completely misses that. So that the fact that the wave is flat until it reaches, until this characteristic information reaches the wave. So we actually have a paper, I'll put it in the chat. We had a paper on this at the Detonation Symposium some years ago. I'll put it in the chat here. That shows just how wrong the DSD theory is when you
it's probably better to send the paper with Qiang as well to by email.
Yeah, I'll
just
send it by email.
Yeah, because this chat might be lost after we end the meeting.
Yeah. So this is what's my concern. As long as the expansion is very, very slow in comparison to the time scale it takes for acoustic or characteristic information to propagate back and forth between the upper and lower walls, then the technique is very good. And this assumption that there's a single curvature or single area expansion applied is correct. But as the ramp becomes the smaller ramp, the greater curvature, then at some point that assumption is no longer valid.
Yeah. This is actually for what we studied this technique. In our experiments we have the large one and small one. For the large one, it's like it propagates like more gradually, since the rate, the divergence rate is smaller. But for the small one, the divergence rate is larger. And we also found we indeed actually in our works we evaluated the deviations of the real real detonation from the quantity 1D approximation at the function of the divergence rate. And for the large ramp, which has the small divergence rate, the deviation is very small. It's negligible. I remember like it's within like 10%. But for the small ramp, this deviation is larger. It's like as you propose, because it's more steeper, and then the expansion wave is it impacts it could impact the assumption. And actually also in our work we found that for the exponential horn it needs some time. It needs a certain length for first the planar detonation front to transit to the confinements. And but the fact is once it transits to adapt to the confinements, then it could propagate in a nicely in a quasi-steady way. But as you propose, the appropriate the deviation of the quasi-steady assumption from or the deviation of the real detonation front from the quasi-steady approximation depends on the divergence, the magnitude of the divergence rates. If it's smaller, it's better. This is why. This is actually we want to. Previously, I was also working on to find to try the other ways for designing this this ramp. We found that if it's a little bit larger, then this won't improve much. And a better solution for this problem probably would involve the the 3D horn, because in our even in our present work we assume the boundary layer as like a constant, but in the 3D then the boundary layer in fact impact could be negligible. Then we could try the small divergence rates like our large ramp, just need one, then could like get more solid conclusion. Yeah.
Yeah, I mean, as long as you, so I think we basically agree, and as long as you acknowledge, you know, that when the ramp gets very, very small, it no longer is quasi steady. Then that's actually quite interesting. You know, you could actually study, that could be another layer of physics, you know, is looking at when it no longer is quasi steady. In a sense, that's very interesting as well. You know, to even go to a steeper ramp or a smaller ramp, you know, you won't obtain a single value of curvature, but you know, you might be able to learn something even more interesting about the detonation dynamics. You know, I mean, this is kind of the interesting thing about the DSD theory, is when does it work and when doesn't it work? And this kind of experiment could tell you that. It could tell you when you can use a quasi-steady approximation and when you can't use it. But I think the interesting parameter to look at would be what I'm showing here is the, oops, I made it go away, is just this time scale, how long it takes an acoustic wave in the post ZND, you could just look at the ZND structure and we did this in the paper that I put on the chat there. You can see how Xiao did this calculation. He looked at, you know, with the speed at which acoustic information propagates back and forth behind a detonation wave, and that sort of gives you a time scale or a length scale as to how that information is communicated. And I think that's the appropriate scale to tell you if you're in the quasi-steady regime, or if it's, you know, if the ramp is very short, then it's probably a fully unsteady problem. So
yeah.
Okay, good. Yeah, I think as long as we agree on that, I think this is a fantastic experiment, and there's probably even more can be learned.
And also, I think it's more there's some similarity, but I think it's a more complex problem than what we considered before. Like you have a fixed size of charge or a fixed size of a reactive layer, and then outside the reactive layer, we have like a inert confinement, right? I think this is more, if you have like very steep ramp, it's probably more complex because the communication time from the boundary to the center of the of your reactive part is larger and larger. So it's gonna take like more and more time for the boundary to be felt by your whole reactive layer, or the center line of your reactive layer.
But what Matej Radulescu argues, I mean, I brought this up when Professor Radulescu was developing this experiment some years ago. I brought up this objection, and you know, he argued that the exponential horn is a simpler experiment because provided you're in that quasi-steady regime, it's governed by just a single value of kappa, right? Whereas when we have our problems, Xiao, where you have the layer, the reactive layer with the loss of confinement, you know, there's different curvatures and there's different time scales, and you don't actually control the curvature. You know, the detonation finds its own correct curvature, whereas in the exponential horn, you can impose the value of curvature, and in principle, it's constant. You know, as long as the exponential horn continues, it's always a constant curvature. So, you know, I like both experiments. I think the reactive layer and the exponential horn are the two best experiments that can be done to look at detonation dynamics. And I would like to see everyone in the community kind of focus around these two experiments. I think that for example, I've talked to Xiao about this. I think for the next ICTERs, it would be wonderful if we could get everyone that does numerical simulations to do these two problems, to do the reactive layer with inert gas on top, or do the exponential horn, and use that as a major benchmark problem, because it's the I think it's the cleanest. These are the cleanest kind of problems that reveal the dynamics of the detonation. Because in both cases, at the end, you end up with quasi-steady wave speed, and you can measure that very unambiguously. You know, I like experiments, numerical and computational, where you just measure one thing, like detonation speed, and there's no ambiguity. It's not like you have to do statistics and you have to do all this heavy analysis. All you need is just see when was the wave here and when was it here, and knowing the distance and the time, you get a speed. and then from that speed you try to extract the physics that's there. So and I wouldn't actually be interested in, for detonation physics, doing any other calculations except the exponential horn, I think, and the reactive layer are the two that hopefully the community would focus on.
Yeah, actually, my future, I'm also planning to do some, because in my PhD, I didn't do the simulation related with the exponential fall. So after, I'm planning to continue this topic for the simulations. Yeah.